In this lesson, we're going to go over Unit 8, Acquisition 3, on weak acid-base calculations. So last lecture, we did strong acid-base calculations, and a strong acid or a strong base completely dissociates. So that means the concentration of the hydrogen ions would be equal to the concentration of our strong acid. Well, we cannot make that assumption with weak acids and bases because weak acids and bases only partially dissociate. They only partially dissociate. So, what we are going to do is a rice table. We are going to use the equilibrium expression. So Ka or Kb, and we could actually use that to represent the extent that a weak acid or base ionizes. So good old rice tables are coming back. All right, let's look at some of the calculations. So first example, let's say you were asked to calculate Ka if the pH of 0.10 molar formic acid was 2.38. So let's start by filling out a rice table. So again, R is for a reaction. I already have my reaction. I is the initial concentration. C will represent the change in concentration. E will represent my equilibrium concentration. So let's fill out what we know. Formic acid has a concentration of 0.10. We're always going to assume that the initial concentration of our products is going to be 0. Reactants will decrease in concentration and has a coefficient of 1, so minus 1x. Products are always going to increase in concentration, and again, they each have a coefficient of 1. So that means my equilibrium concentration would be 0.1 minus x. 0 plus x is x. 0 plus x is x. So normally when we do rice tables, after we fill out the rice table, step 2 is to determine x. We need to solve for x. X is equal to the hydrogen ion concentration. I know the pH. If I know the pH, I could solve for H+. H+ is going to be equal to X. pH is equal to the negative log of H+. H+ is equal to 10 to the negative pH. My pH is 2.38. So now I can figure out the hydrogen ion concentration. 10 to the negative 2.38 gives me a hydrogen ion concentration about 4.2 times 10 to the negative third. So this is the concentration of H+. The concentration of H+ at equilibrium is equal to X. This is going to be X. Now I could solve for my equilibrium concentration of everything else in my reaction. So formic acid. At equilibrium, the concentration would be 0.1 minus X. Alright. Concentration is equal to X. X equals 4.2 times 10 to the negative third molar. So I now have my hydrogen ion concentration, formic acid concentration. Once I have all of my concentrations at equilibrium, now I can write my Ka expression. I can plug in my equilibrium concentrations and I could solve for Ka. Let me put the reaction up really quick. Products over reactants, so Ka is equal to products over reactants, each raised to the power equal to their coefficient. In this case, everything has a coefficient of 1, so no exponents. Let's plug in what we know. And solve. When I solve, I get 1.8 times 10 to the negative fourth, which is what we would kind of expect. Remember, this is a weak acid. Weak acids have small Ka values less than 1. So this tells me the extent to which the weak acid dissociates. The larger the number, the more it dissociates. The smaller the number, the less it's dissociating. Let's do another example, but for this one, instead of calculating Ka, you're going to calculate pH. Let's say you were asked to calculate the pH of acetic acid if its concentration is equal to 0.30 molar and its Ka is 1.8 times 10 to the negative fifth. So we can, I need to give you a balanced reaction. So we can start with our rice table. Let's fill in what we know. I have the concentration of acetic acid. Always assume, unless you're told otherwise, the initial concentration of the products is 0. Reactants are going to decrease in concentration. Products are going to increase. We would bring down any coefficients. They're all going to be 1. I don't know what the change in concentration is, so I'm going to call that x. Initial plus change equals equilibrium. 0 plus x is x. So I have a Ka value. So let's write our Ka expression. Products over reactants and let's plug in what we know. Ka is 1.8 times 10 to the negative 5th. Remember, this is an equilibrium expression, so we're only looking here. So I'm going to have x times x, we can call that x squared, all over 0.30 minus x. Right now, if we were to solve this, it's going to be complicated. So we are going to make an assumption here. We are going to assume x is negligible. We're essentially just going to ignore it. The reason why we can ignore it is Ka is very, very small. So we are going to assume that the change in concentration, that x, is going to be much smaller than our initial concentration. So let's say our change in concentration was very, 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 very small. 0.30 and 0.30 minus a really, really, really small number are going to be almost the same. It's not going to make much of a difference. So we are just going to assume x is negligible, pretend it doesn't exist. Now this makes your math much, much easier. So let's multiply both sides by 0.3. So 1.8 times 10 to the negative 5th times 0.3 gives me 5.4 times 10 to the negative 6 is equal to x squared. To solve for x, we can take the square root of both sides. And I get like 2.3 times 10 to the negative 3rd is equal to x. So remember, we are trying to calculate pH. Well, how do I calculate pH? pH is equal to the negative log of H+. The concentration of H+ is equal to x. So not only is this the concentration of x, this is also the concentration of H+. So if I want to solve for pH, I'm going to take the negative log of x. And I get my 2.63 as my pH. All right, let's go back and talk about why we can assume x is negligible. It's not always negligible, and this comes down to what's called the 5% rule. So what we're going to do is take x and divide it by the concentration of the weak acid. We solved x to be 0.0023, 2.3 times 10 to the negative third. And let's divide that by the concentration of the weak acid. The concentration of my weak acid was 0.3. 0.77%. If this is less than 5%, x is negligible. Again, if I could spell, x is negligible. And again, the reason why is because it's so small. X is representing our change in concentration. If our change in concentration is small, it's not going to make a big difference on your pH. So again, another way to kind of explain this. The change in concentration is minus x. So let's say I did 0.3 minus x. 0.3 minus 0.0023. 0.2977 rounds up to 0.3. The numbers are so similar that it's not going to make a big difference in your calculation. So to make your life easier, assume that x is negligible.